squared. All right. So this one is a sample size for mean. The other one asked about is a sample size for proportion. Oops, that's the wrong problem. I must not have copied correctly. Let me undo, go away. All right, let's try it again. Let's just do a screenshot maybe. Okay, so SAT scores are distributed with a mean of 1,500, standard deviation of 300. You're interested, and your numbers may be slightly different, keep that in mind, in estimating the average SAT score for first-year college students. You would like to limit the margin of error of your 95% confidence interval at 25 points. So they're telling us what the margin of error should be. How many students should we sample? All right. So in this case, what do we know? Information that's given up here, this is my mu of the population. This would be my sigma for the population. This is my confidence level. And here they're giving me the error bound on the mean, and they're saying, hey, what sample size would you need to get results around a 25-point margin of error for students at some particular school of what their SAT scores are. The margin of error formula, given that we know the population standard deviation, is going to be the appropriate z-score, which is based on the confidence level, sorry, excuse me, times the population standard deviation over the square of the sample size. So we need to solve this, and in the book in section 8 point, I want to say 8.3, but I'll have to double check. They solve this formula for you. So I'll just do that right now. So I'm just going to call the margin of error, let's call it E for simplicity. If I want to solve this for n here, I would have to, let's say, divide z and sigma to the other side, because I want to get n alone. So just a little algebra, jiggery pokery here. So that gives me a left on the other side, n in the denominator. So 1 over the square root of n equals E over z sigma. And then to get n in the top, I can just flip both sides. So then the square root of n is z times sigma over the margin of error, and then take the square of both sides to get rid of the square root. Excuse me, sorry about that. Allergies. So then basically everything here is squared. So the sample size is related to the square of the z-score, which comes from the confidence level, times the square of the standard deviation of the population over the square of the margin of error. And we usually call that the error bound on the mean. So that's sucker squared too. And I just have to calculate the z-score. I know the other things, right? So I know sigma is 300. So I'm going to have a 300 squared. I got to figure out what the z-score is. I'll do that in a minute. And the error bound, they're saying make it 25. So we'd have a 25 squared down there. The z-score, let's whip that out in stat key for 95% confidence interval. Let's reset. Has a z-scores have a mean of 0 and a standard deviation of 1. So that's the default page you get to there. And then just set your confidence level 95%. So they say the z-score should be about 1.96. So this z should be about 1.96. And then we got to square it, right? Everything gets squared there. If you wanted to get the z-score on a spreadsheet, we would need alpha over 2. So remember, alpha is always 1 minus the confidence level. Oops. Which in this case would be 1 minus 0.95, which gives me 5%. And then we cut that in half. Alpha over 2 would then be 0.025. And to get the z-score for that percentage, that's the norm inverse. So 0.025, comma 0, comma 1. And the spreadsheet's going to say, yeah, that's about negative 1.96-ish. And it'll give you some more decimals. It's like 957-ish. I can't remember all of them. But and because I put in the left tail here, it gives me the negative version, but we plug in the positive version when we're doing margin of errors. So again, I need to know that formula there. And really the only way stack key can help is just it gives us another way to get the z-score. Otherwise, I can't get much out of stack key besides that. So now we just need a calculator or a spreadsheet to figure out what that is. So for my particular problem, I would have that 1.96 squared times the 300 squared divided by, what was it, 25 points for the margin of error, so divided by 25 squared. Holy shit. I mean, oh, that's not too bad. Sorry, I thought that was a comma in there. Oh wait, no, I mistyped something. I have a comma in my, oh, interesting. How did it interpret that? Let's try it again. Oh, it came out the same. It interpreted the comma as a decimal point. Thank you, Google, for fixing that for me. Yeah, so this says, and you always round up, even though, right, a 1 there would say don't touch the 3. But here, we always go to the next person up. Otherwise, our confidence, our margin of error might be smaller than we want. So we always go for another person. So I would say we would sample 554 people to get a margin of error that's around 25 points from the mean. So 554 people should be sampled. That should be about my N. All right, so the next one was how do we find estimated sample size for a proportion? And let me get myself a little green check. Yeah, I got it right. And again, you should try a similar question if you just did this with me. So number 12 is the other one. And please tell me I remembered to push record. I did. Number 12 is similar, but for a proportion. So let's grab that. And I recorded one of these the other day too, and wrote down all the formulas. So new page, please. So political candidate asks us to conduct a poll and determine the percentage of people that support her. The candidate hopes for a 2% margin of error to estimate that. So maybe, right, we do run a poll and it comes out to be 46%. That means our margin of error of 2% means 46% is the middle. So the people that approve of her or support her is somewhere between 44 and 48%. At a 90% confidence level, what's the sample size? So the error bound on a proportion is equal to a z-score times the standard error for a proportion, which is the square root of p prime times q prime over n. And the other day I did the algebra to solve this right here. Let me see if I can get that right. If we solve this for n, then what's going to happen? We're going to get n equals z squared over the margin of error squared, and then times p prime times q prime. I'm fairly certain I got that right. Let me look at this again. I don't feel like doing all the algebra. I'm trying to do it in my head. N goes up, that goes down, those stay still. And we have the square stuff. Yeah, that was right. Problem here is we don't know a previous estimate of the number of people that support her. So the safe thing to do that if no other information is known, so if no previous proportion is known, then what we do is assume 50%. Because that means Q prime is also 50%. Then you run the sample and you see what it actually is, but this gives you a better estimate in the upper area of how many people to survey, regardless of what it's going to really come out to. So that's the safe way to go. And then we have to find the z-score that goes with a 90% confidence interval. So on a so 90%, right, that just means if 90% is in the middle, 10% is split, so there's 5% in each tail. So we need a z-score that goes with a 5% tail. Come on, Pen. So on a spreadsheet, that would be z sub 0.05, my alpha over 2, and that's the norm inverse I mentioned in the previous one. 1.645. That does sound correct. Yeah, and we can whip that out in stat key too, which is nice, but that does sound like the right one. Thank you, Charlotte. So then we would have the 1.645 squared times our 50% guess at P prime, which makes Q also 50%. And then we divide by what she hopes for a margin of error, which as a decimal, it's got to be a decimal, so that would be 2%, and that's got to be squared. So the z-score gets squared, the margin of error gets squared, and then we get P prime times Q prime there. So then we whip that out on a calculator. So I'll just use a regular calculator, I think. So 1.645 raised to the second times 0.5 times 0.5 divided by, she wanted 2%, so 0.02, and that's going to be squared 2. I think that looks right. So this says I would have to sample, and we always round it up, so 1,692 people is what we would go to here. Oh, 1,692 is what we would round up to. So regardless of how small the decimal is, always go to the next whole number. That's a pretty big one. So samples of that size would be like this. This must be like for a governor. That's a lot of people to survey. Okay. What time is it? 11:04. Okay, so this is a good stopping point here. I'm going to stop the video.